All right, so we're going to go over page 638 and the 10.4 review. Again, I've sent these out via just PowerPoint to you guys, but this is more, if you need kind of some clarification on a specific question, feel free to just skim through this video and find the question that you feel like you need some extra help on and listen through to the explanation that I give. And as always, if it doesn't really suit you, if you think you need a little bit more explanation, please feel free to reach out to me or reach out to a classmate and see if you can get a little bit more clarification. So here we go with page 638. We're going to start with number 8, which was a compare and contrast question. It asked how the relationship between the areas of two congruent figures differ from the relationship between the areas of two similar figures. I tell you guys this in class all the time. Please don't just like copy and paste what I have on my PowerPoint, but your answers are going to vary. Everyone's answer to this will look a little bit different. You might say something like the areas of two congruent figures are going to be exactly the same, while areas of two similar figures are going to have a relationship of a squared to b squared, or something like that. Maybe you want to make a t-chart, maybe you want to make a Venn diagram. You can do anything to kind of describe what's going on with these relationships here. So number 9 and 11, and notice I actually went through and did the evens on these two, which was an accident, but it might be just kind of nice if you want to glance around and get some ideas of some questions that are similar, right? How do we do those types of questions? So on number 9, it asks us to compare the first figure to the second, give the ratio of the perimeters and the ratio of the areas. So on number 9, we're looking at to find the ratio of the perimeters, right? We're finding just the scale factor essentially. So 2/4, which simplifies to a half. Remember, we want to simplify those guys. And then to find the ratio of the areas, we just take our scale factor or our perimeter ratio and we square it. So 1 squared over 2 squared just turns into 1/4. On number 11, again, we're looking at our scale factor here, 14 to 21. That simplifies down to 2/3. And then when you square both of those to get the ratio of your areas, you should get 4 to 9. If you want to glance over here at 10 and 12, for number 10, the perimeter ratio of the perimeters was 4/3, and then square that, you got 16/9. Number 12, again, take those numbers for the scale factor to find the perimeter ratio, and I got 3/5, square them, and get 9/25. So 13 and 15 here, it said that the figures in each pair are similar. The area of one figure is given. Find the area of the other figure to the nearest whole number. So you'll see in number 13, they tell us that the area of the smaller parallelogram is 6 inches squared. We want to find the area of this unknown parallelogram here. So I'm going to start because I know these numbers here, right? I know 3 and 6 for the ratio of the perimeters. If I start by finding the ratio of the perimeters, which is 1/2, and square it, I can find the ratio of the areas, and then I can go down and set up my proportion, right? My known ratio of the areas is 1/4. I don't know my actual areas, but I know they should also be in a ratio of 1/4, so I'm just going to make them equal there and figure out, right, what's going to work to fill in that question mark. So you could either do mental math for that, or I would cross multiply them, right, and say 1 times a question mark equals 6 times 4. And you should end up getting 24 inches squared for this area for number 13. I'm going to skip down to number 15 here, but again, feel free if you want to check out 14 and 16, go ahead and do that, and they might just be some good extra practice problems for you. On number 15, they tell us that the area of the larger triangle is 105 feet squared. And notice again that they give us side lengths, but we don't have any other side lengths. We don't have any angles. We don't have anything to figure out like approximate times perimeter or anything like that. So we're going to have to go to these area ratios here. So if my area here is 105 feet squared and I don't know this area, as usual, I'm going to find the ratio of the perimeters, which is going to be 4/3. When I simplify it and then square that, I get 16/9 for the ratio of my areas. So like we did in our notes, we're going to set up a proportion here, 16/9, and then the proportion that I don't know every piece to is the actual proportion, right? I know that my actual area of the larger triangle is 105, but my smaller triangle, I don't know the area of that one, right? So I'm going to cross multiply and solve, and I get that x is equal to 59 feet squared approximately. So again, we're just doing odds here, but you can take a look at number 18 if that helps. 17 is a question that people tend to get a little bit stuck on because they of the cost instead of just like an area. So the way that I think of it is the cost is basically the area, right? So we're talking about 216 to refinish a smaller floor. So we're saying for that smaller wood floor, maybe you could say it's like $1 per square foot or something, right? So it's 216 square foot, for example. So the scale factor of the dimensions of two wood floors is 4:3. So that's really the ratio of the perimeters. So then the ratio of the areas is going to be 16 to 9. And I promise that's a 9. It got kind of cut off. So my larger floor has an area ratio, or that part of the ratio is 16. The smaller part of the ratio is 9. So then if I think of 216 as kind of like the area, representative of the area of the smaller floor, and then I don't know the area of the larger floor, I'll use that as x on top so that it matches up with that larger number. And then I'm going to cross multiply and solve for x. And I get that x is equal to 384. Okay, so that would be the cost of the larger floor. So same thing down here on number 18. If you're kind of feeling a little uncertain on 17, 18 is the same type of problem. It tells us that an embroidered placemat costs $3.95. So you could think of it as maybe like cost per square inch. That would be a really big placemat, but would be $3.95, right? A cent per inch, or maybe $1 per inch, and it's 3.95 inches squared. An embroidered tablecloth is similar to the placemat, but it's 4 times as long and 4 times as wide. So we're talking about the lengths, right, of the sides. How much would you expect to pay for the tablecloth? So again, we're going to have our ratio of our perimeters will be 1 to 4, and then the ratio of our areas, if we square that, will be 1 to 16, right? So basically, we're saying that this area, or this cost of this larger area, is going to be 16 times as big as the smaller size. So I can set up my ratio here and solve, and I got 63.20. 19 and 21, and then 20 is kind of a bonus in there. Find the scale factor and the ratio of perimeters for each pair of similar figures. It gives us 2 regular octagons and their areas. So I know kind of right off the bat that the ratio of the areas is 4 over 16. But if we're just trying to find the ratio of perimeters, I can just take the square root of that and I get 1/2. And you'll notice that I kind of waited until the end here to simplify. It would be just as easy to say, oh, 4 over 16 is equal to 1/4, right? So the ratio of areas is actually 1/4. And then when you take the square root of 1/4, you're still going to end up with 1/2. And then remember that that's both the scale factor and the ratio of perimeters, right? Because those guys are equal to each other. On number 20, I'll just do this one as a bonus real quick. We have 2 triangles with these areas. So again, if I plug those in there and then just simplify them, that simplifies to 25 over 4, which can easily be simplified with the square root to 5 over 2. And then 21, which was actually assigned, 2 trapezoids with areas 49 centimeters squared and 9 centimeters squared. Again, I'm going to make my ratio of the areas, which is 49 over 9, and then take the square root to simplify it, right? So I just get a over b, which would be 7 over 3. So next is number 25 and 26. The scale factor of 2 similar polygons is given, and you just want to find the ratio of their perimeters and the ratio of their areas, which should be really fast, right? Ratio of the perimeters is just going to be exactly the same as the scale factor, and then the ratio of the areas, you'll just square it, right? So you could also write this one as just 3 and 9, since it's divided by 1, and then 2/5 squared turns into 4 over 25. On number 57, we're finding a pentagon, the area of a pentagon with the apothem 13.8 and a side length of 20. So as always, I've kind of mentioned this to you guys several times. Make sure that you find the length of the perimeter and don't just use the side length. So we're going to do, because it's a pentagon, 5 times 20. So we have a perimeter of 100. So now we'll go 1/2 apothem times perimeter, and we get 690 units squared, because it didn't give us any units over here. And that was just some review. 60 and 61, again, are some review. So we're going to find the area of each regular polygon. On number 60, because it's a square, we could draw in our radii and use 45, 45, 90 triangles, but I noticed that with the apothem, if I just double it, right, if I find the apothem in the other direction, that's equal to the length of the side. And since it's a regular polygon or a square, I can just do base times height. It's just going to be 6 times 6, or 36 meters squared. So if you do it with the radii and the special right triangles, I would say that's kind of the hard way to do it, but you should still end up with 36 meters squared. So check your math there. On 61, we have a hexagon with 6 sides. We have a length of 42 inches for the side length, and then an apothem of 36 inches. So I kind of sketched in my radii here and then realized, you know what, I don't actually need that radii because I already have my apothem and I can find out my perimeter. So my perimeter was 252 inches, my apothem was 36 inches, and just plug it into the formula, you get 4,536 inches squared. And that's all for that first worksheet. So moving on to the 10.4 review worksheet, we've got the 10.4 perimeter and area of similar figures review. So 1 through 4 should be pretty quick, and you guys can just kind of disregard these highlighted things. I sometimes will put those there just to remind me to mention specific things to you guys. So on number 1, we find that our scale factor was 3 over 6, which simplifies down to 1/2, gives us our area ratio of 1/4. Number 2, make our scale factor 8 to 6. So my perimeter ratio will be 4/3 and the area ratio 16/9 when I square it. Again, we have our scale factor given here. Perimeter ratio is the same. Area ratio, square it, you get 4/9. Number 4, the perimeter ratio again is the same, and then the area ratio, square it, would be 49/16. On 5 through 7, these are the problems where we have the areas of two similar figures and we want to go backwards to find the scale factor and perimeter ratio. So a really key thing here on many of these problems is going to be, do you remember to simplify, right? So on number 5, I actually could simplify that a little bit earlier, but I just went ahead and left it and took the square root of it there, right? So this is like a squared and b squared. If I take the square root, that simplifies down to 12/6. And then 12 divided by 6 is just 2, right? So my scale factor and perimeter ratio would just be 2/1 or 2. But I could go back at the beginning. I believe I could divide those both by 12 and I would get 12/3. I could simplify that even further to 4/1, right? So then when I take the scale factor of 4/1, it's going to turn into 2/1 again. On number 6, we have two rectangles with the areas of 72 and 50. I could take the square root right there, but those are not perfect squares, 72 and 50. So I'd have to do some simplifying the radical, which I'd like to avoid at all costs. So if I simplify those first, 36 and 25 are both perfect squares. So when I take the square root of those areas, I get 6/5 for my ratio of perimeters and my scale factor. So for both of those guys. And you notice, right, these are all the same, right? Scale factor and perimeter ratio are always equal to each other on all of these problems. Number 7, we have two regular octagons with areas 147 and 12. So again, 147 and 12 are not really nice numbers to deal with as far as square roots go, but if I divide them both by 3, I get 49/4. And then I can take the square root of those and get a really nice fraction, 7/2. So that's my scale factor and perimeter ratio. Okay, so on these ones, we're looking at similar figures, right? So we've got two hexagons here. We have the area of one figure that's given and find the area of the other. So on number 8, if we knew that these were regular hexagons, which it looks like they are, then we could go through and find the apothem and do the perimeter deal. We actually don't know that these are regular though. So unless we know that for certain, we can't use our 1/2 apothem times perimeter formula. So I'm going to start by finding the ratio of my perimeters, which is 11/3. Square that, my ratio of my areas is 121/9, and then I'm going to set up a proportion. So 121/9 equals my unknown area over 27, my known smaller area. Cross multiply those guys and you should get the x equals 363 meters squared. On number 9, same idea. So I don't know that these are regular. I don't know any angles. I don't know anything. So I'm just going to use my ratio of the perimeters here because I know that they're similar. So my ratio of perimeters simplified turns into 2/7, which squared gives me 4/49 for the ratio of my areas. So for my proportion, I'm going to do 4 times 294 and then 49 times x. And you'll notice I made a typo here, so I had to cover over it with some typing. And then divide both sides by 49, and you should get that x is equal to 24 feet squared. Number 10, it tells us that we have the longer base of a right trapezoid is 12 feet. The longer base of a similar right trapezoid is 30 feet. The area of the smaller right trapezoid is 20 feet. What's the area of the larger right trapezoid? So you guys, usually when you see these and you're talking about similar shapes, anytime in this chapter when you're talking about similar shapes, you're going to want to go straight to ratios rather than trying to plug everything in and find the areas. So here, the ratio of the perimeters, right? If I look at the longer base of a right trapezoid is 12, and then the other longer base is 30, those are corresponding sides. So I can put those into a ratio, which simplifies to 2/5. And then when I square that, it's going to be 4/25. Sorry, that got cut off there, but that should be 4/25. So then if I know that the area of the smaller right trapezoid is 20 feet squared, and I don't know the larger one, right? If my ratio of areas is 4/25, smaller to larger, well, my smaller area is 20, I don't know my larger, so there's my proportion. I can cross multiply and solve, and I get 125 feet squared for the area of the larger right trapezoid. Similar problems on 11 and 12, haha, no pun intended. A regular pentagon has a side length of 24 centimeters and an area of 135. So kind of keep organized here, right? We're talking about a length and then an area. And then another similar pentagon has a side length of 8 centimeters. What's the area of the smaller pentagon? So if we look at our side lengths that we have here, right, we have 24 and 8. So I'm going to make those into the ratio of perimeters. That simplifies to 3/1, or you could just say 3 also. And then square it to get the ratio of the areas would be 9/1. So then I can set up my proportion here, right? An area of 135 centimeters squared. Then I can cross multiply, I get x is 15 centimeters squared. Number 12, we have a rhombus with a side of 6, and I actually sketched this out to kind of keep it clear for me. A rhombus with a side of 6, another one with a length of 15, area of 60, unknown area for the larger one, right? So I'm going to find my ratio of perimeters is 2 over 5, square it, 4 over 25 for the ratio of the areas, set up my proportion, I get 375 meters squared for number 12. Okay, so on number 14, we're just going through on all of these and finding the areas of these polygons. On number 14, we don't know the height of this shape unless you kind of look into that triangle there. So since this is clearly a rectangle with our right angle, and that's a length of 6 feet, that means that this triangle has kind of this base here of 4, which, yes, this is totally not to scale. But if I use the Pythagorean theorem, or notice that this is just a 3, 4, 5 foot triangle, then this length, this height of the trapezoid here, or the height of the triangle, will be 3 feet. So that's going to be really important, right? And then we plug it into our formula, 1/2 height times base 1, 6, plus base 2, 10. I have kind of a little mini simplifying work shown here, and then my area will be 24 feet squared. Number 15, we have a regular pentagon with an apothem of 3 centimeters, side length of 5. So make sure you find your perimeter there. Remember that pentagons have 5 sides. That's something a lot of people missed on the quiz, thinking it was 6 sides. So the equation will be 1/2 apothem perimeter. You get 37.5 centimeters squared. Number 16, this was actually a really commonly missed question on the quiz, was this is the side length of the rhombus, not part of the diagonal. So if this diagonal is 12 feet, remember rhombuses have perpendicular diagonals, and so you're going to have to do the Pythagorean theorem, right? Or I recognize that this is a 5, 12, 13 Pythagorean triple, so you could use that also. So that means 5 and 5, we have diagonal 1 is 10, and then 12 and 12, diagonal 2 is 24. So we can plug those in and get an area of 120 feet squared. On number 17, pretty straightforward, right? We have our 2 diagonals there. Plug it into the formula, you get 72 feet squared. On number 18, we have a 30, 60, 90 triangle we kind of have to pay attention to here. So with a length of 4 here, if it's 30, 60, 90, remember that the short leg is going to be half of the hypotenuse. And then the long leg of a 30, 60, 90 is the short leg times the square root of 3. So there's the height of our parallelogram. And then the area of a parallelogram is just base times height, right? Just like a rectangle. So it ends up being 14 square root of 3. On number 19, we're looking at a regular hexagon. We have a side length of 10, which means my perimeter is going to be 60, right? Because it's 6 times 10. To find the apothem, remember that in a hexagon, this is a 30, 60, 90 triangle, right? And you could draw in your radius and prove that that inside angle is 60, split it in half with the apothem, you get a 30-degree angle there. So if this whole length is 10 and the base length is 5, right, because we have half of 10 gives us 5 for the base of that triangle, that means the apothem is going to be 5 square root of 3. Okay, then we do 1/2 apothem perimeter, we get 150 square root of 3 meters squared. All right, so our last section here is trigonometry review. Remember that this comes from section 8.3, so I would recommend if you feel kind of stuck, maybe go back to 8.3 and look at some of those problems. So on number 20, it looks like from my known angle 13 here, I'm using my adjacent side and my hypotenuse. So I used cosine, right, adjacent and hypotenuse. Cosine of 13 equals adjacent 53 over hypotenuse x. Remember, just like I showed you guys in the video, that these are the ones where you're going to have to multiply x on both sides to get rid of that x in the denominator, and then divide both sides by the cosine of 13. So before you kind of get to your final answer, your calculator ready answer, which I just didn't have space on my PowerPoint here, but you should have 53 divided by cosine of 13 equals x. So that's approximately 54.39. On number 21, 35 is my known angle, so x is opposite, 15 is adjacent, that gives me tangent. Opposite over adjacent, x over 15. Remember, you're going to want to multiply both sides by 15 to get rid of it. So you have x equals 15 times the tangent of 35, and that gives me 10.50. Remember, we're going to want to leave that 0 there, even though I think it was like a 1 or a 2 that came after this, so we don't round it at all, right? It just stays as a 0, but that tells other people that we've thought about it out to a 0. On number 22, I'm using tangent again, opposite over adjacent, 6 over 5. This time I'm trying to find x though. So remember, just like I showed in the trig review video this week, that we're going to have to do the inverse tangent on both sides. So kind of our calculator ready answer, I made it really small here, would be x equals inverse tangent, or that tangent -1 of 6 over 5. And your calculator is going to look a little different on that one. So it's 50.19. On 23, I know 72, opposite over hypotenuse, x over 54. Multiply both sides by 54, and I got 51.36. 24 is another angle one, so we're trying to find x here. Opposite over hypotenuse is going to be sine again. Use inverse sine on both sides to cancel it out over here, so I get x by itself. So it's equal to inverse sine of 7 over 23. I get 17.72. I want to say I rounded that up, that number. Again, on 25, we're finding an angle. This one I used cosine, adjacent over hypotenuse. So cosine of x equals 15 over 22, and x equals 47.01.